I'm in my front yard. It's just starting to rain. So the rain's hitting the driveway and it's starting to run off there. On the driveway, not much is taken up by the ground. It's also raining on the grass here. And so that doesn't have as much runoff, but it'll eventually fill up. So it's starting to fill up. It'll eventually fill up, I guess, and it'll be runoff. And then I got mulch here, and I got flowers there. And then it's running down here along the road to the stormwater grate down here. And the question is, can I predict how much is going to run off and how fast it's going to run off? To know that, I could do the physics on every square centimeter of soil. I can't do that, but so I need some type of equation to roughly estimate how much is going to run off of the inches that it rains, how many inches of that are going to run off, and then how fast it runs off. You see, that's going to depend on the slope here, pretty steep slope coming down. It's going to depend on the ground surface here, and a few other things. So that's going to be our next section, is to try to come up with a way to make predictions on how much will run off, so then we can then do what we need to do. Do what we need to do to manage that runoff.
Okay, we're finally going to get to it. We're going to go through the calculations for runoff. I have this PowerPoint that you can follow along with. I've divided it up into, this first part will be an introduction to the rational method, and then we'll go to the NRCS method, and then after that I have an example you can work with, the calling of the church example. We'll do that in a few parts. So this one, you have the PowerPoint available. You also have a handout that looks like this. You can take notes on that. So it's not an assignment that I'm collecting. That's just for your use. If you want to use that for notes, we will go through this and fill in this in the PowerPoint. So back to here. So I will acknowledge my colleague again, Finley Edwards, who I stole some of his slides for this. So I'm going to start off this with this is the cover of the Highway Hydrology Manual, and just shows the concepts of what we're talking about here. So we're going to calculate the runoff that comes from precipitation. Some of the rain is initially taken out. We call the initial abstraction before it starts running off. We have the storage on the land, so that's what doesn't run off, and that fills up over time after the initial abstraction. And then it gets to the water body. We'll talk briefly later about routing and some of the losses along the way. Well, we've talked about that a little bit so far. So the calculations, I decided to go back to this. I think I put this in the syllabus, but the stormwater management, and this was specifically from the Pennsylvania BMP manual, but this is in general, that the tradition is that there would be no increase in the rate of runoff. That's the peak flow, and the rate of no increase after development. But then now we're moving to, we have to the rate of flow, the volume of flow as well. Groundwater recharge, so that's why we did a little bit with groundwater. We need to know a little bit about that, about infiltration. Water quality, we'll do an exercise later on some calculations that will help us ensure water quality. And then we will again do the unit on stream restoration and stream morphology. So for example, what methods do we use to calculate the runoff? Well, first of all, for the peak rate, this is an example from the Monroe, Pennsylvania township. We did a student project in that township, and almost all municipalities in Pennsylvania pretty much take their stormwater regulations from the Pennsylvania BMP manual. So they're all pretty much the same. So the requirements are there that you calculate the pre-development and post-development peak runoff rate for the 1, 2, 5, 10, 25, 50, and 100-year storms. How do you do that? It should be determined by using the rational method for watersheds less than 15 acres, and for larger watersheds, the latest version of the technical release number 55 Urban Hydrology for small, that's the NRCS method, and then there's a peak. The NRCS method is a volume method, and then there's a peak method built on top of that, or an acceptable engineering method. For the volume calculations, again from the same document, estimate the increased volume runoff for the 2-year, and this is the 2-year 24-hour storm event, using the cover complex curve number method. This is, and I put the parentheses in, this is the NRCS volume method. So it gives us the inches of runoff. That's guideline 1. So first of all, you determine if you're under guideline 1 or guideline 2. Guideline 2, which by the way, it's if you're under guideline 2, you're exempt from peak. That's the way I understand it anyway. There might be a few exceptions to those being exactly the same for each site. So you have some eligibility criteria. Less than 1 acre, you can use guideline 2, which is the simplified method. And that's, you capture 2 inches, and then 1 inch of that's released slowly, 1/4 recommended for reuse, 1/4 recommended for groundwater recharge or infiltration from generalized water budget analysis. So really, for less than 1 acre, you just have to ensure that you are capturing those 2 inches, and then you have to release half of it slowly, and you got to get rid of the other half of it. So let's talk about the rational method. So the rational method again is used for the peak rate, and the rational method, and this is from, you can find, I recommend the Highway Hydrology Manual. I've mentioned this before as a reference if you want it. This is generally used for drainage areas of 200 acres or less, small sites especially. So in the Monroe Township, again, which I think is probably the same as all of Pennsylvania, it's 15 acres or less. You use the rational method. The rational method says the flow, Q, that's the peak discharge, cubic feet per second, or acre inch per hour. Wait a minute, we'll get to that in a second. Is equal to a runoff coefficient, which I'm saying is unitless at this point, but we'll come back to that, times the rainfall intensity times the area. All right, so this is the equation, Q equals CIA. Let's do a little exercise here on these calculations. You can work on that sheet, or you can just watch the PowerPoint here. Let's say you've never heard of the rational method, and you want to calculate the runoff rate, the rate of flow from 1 acre parking lot, for example. And so we say if it rains 1 inch per hour continuously on 1 acre, and all of it runs off at a steady state, what is the flow coming off in cubic feet per second? So if I take 1 inch per hour times 1 acre, I should be able to calculate a rate of runoff. And if I convert units on that, so 1 acre times 1 inch per hour, convert units, hours to seconds, acres to square feet, inches to feet, I come up with about 1 cubic foot per second. So 1 acre inch per hour is 1 cubic foot per second. So going back to the rational method, I said we get a Q in cubic feet per second is C times I inch per hour times area in acres. How do I get a cubic feet per second? So, and by the way, so this says if it all runs off, that correlates to a C of 1. So really, the units of C, I said unitless before, I guess you could say the units of C, if you take Q in cubic feet per second, are cubic feet per second per acre inch per hour. So C is really the fraction that runs off. So that equation Q equals CIA, we take the intensity times the area, we multiply it by the fraction that runs off. That's Q. That's it. That's the equation. That's the whole equation. It's pretty simple. So those C values, again, this is the fraction that runs off, you are different for different soil types. Why different soil types? Some soil types are better drained than others. So if it's a well-drained soil type, the water is going down into the soil. If it's not well-drained, it's running off the soil. Higher slope, if you look at the numbers here, higher slope gives you a higher number, higher fraction running off. Okay, that makes sense. Higher slope, it runs off faster. And then the land use will give you different numbers. So there are a lot of different tables for these you can find different places. This is from a textbook, gives a description of area and the runoff coefficient, gives a range. I've said before, everything in hydrology is a range of values. This is from that same textbook. This is from the Highway Hydrology Manual. So you look up in a table somehow and you get the fraction running off, the C value. All right, so with Q equals CIA, where do we get the I? Well, the I comes from an IDF curve or IDF table. So I need to have the D, the duration, and F, the frequency, to come up with the I. So the D, the duration of a storm, must be equal to the time of so what duration do I use? So I said it rains 1 cubic foot per second, but what duration was that for? So the duration we use for this is from something called the time of concentration of a watershed. This is really the trickiest part of the whole thing, is the time of concentration. I literally have a book on the time of concentration. On the examples we're going to do, so there's a, we'll do in the church example, we'll do an example, and then there's also a little homework assignment that has one rational method problem and one NRCS problem. And I just give you an equation in the rational method problem to calculate the time of concentration. But let's define what it is here first. The frequency typically specified by the code often requires 1 through 100 year frequencies. We saw for development in the Monroe Township, you had to do it for each frequency from 1 to 100 year. All right, so the time of concentration, you'll see this put different ways. T with a sub C, sometimes a capital T with a sub C, or TOC, is the time needed for a surface runoff to propagate from the most hydraulically remote point in the watershed to the point of analysis, the outlet. And that's kind of, what is it? The longest hydraulic path. So the idea is wherever a raindrop hits the watershed, so the point, we're looking for the peak runoff at a certain point. The outlet of our site, the bottom of our site, some place where it enters a stream. We look at what is the longest it would take a raindrop to hit our site and get to that point. That's our time of concentration. Hydraulic path is the path that requires the greatest time of travel. It doesn't have to cover the greatest distance. So commute to work, well, someone might live 30 miles away but be right on the highway, and someone else might be 10 miles away, but lots of curvy roads and intersections, it takes them longer to get it. So it's the one that takes the longest time to get there. So here's the idea. So we're looking at, for a watershed, we want to come up with the runoff peak rate at this point here at the outlet. When it starts raining, the water near the outlet starts running off, and then as it rains, the water from up farther in the watershed has time to get to that point. So finally the water from the farthest point, which might be the farthest in time, which might be the farthest in distance, or it might be, a point here that's has a really slow flow path or a windy flow path to get there. So when finally the whole watershed is contributing to the runoff, that's the time of concentration. Got another graph here. This is from a textbook. So if it just keeps raining at a certain intensity for a long time, at first, again, the water near that outlet is running off and hitting that outlet until it gets to a point where the whole watershed is contributing to it. That's the time of concentration. I think this one is a better way to look at it. So if I have a rainstorm here, it starts raining and then it stops, the water is running off, there's a time to peak that depends on how long it rains in the watershed. That's not a quick calculation. The time of concentration is not the same thing. So the water stopped raining here. The water that hits the farthest place there is the last to run off. So the time of concentration is when we're back to, at this point here, this is the point where we're back to the base flow, and there's no more runoff. The frequency is usually specified by the code or the design manual, so different projects might specify different design frequencies for the runoff we have to calculate. For development, typically you have to do it for all of these storms. If you do it for the 100-year storm, doesn't that cover the 1-year storm? It's a question I always have, how that works. All right, so let's do a little example calculation. This again is in that handout sheet. You can work it there, or you can just kick back and watch the PowerPoint. It's up to you. I'm not collecting it. All right, so we are required to design for the runoff from a 10-year storm. So that's given. Our frequency is given. Location is central Pennsylvania. Why does it matter? Because the IDF curve is going to be different in different places. So I have to know which curve to use. Drainage area, we're going to do the runoff for 40 acres. Wait a minute, aren't we supposed to use the rational method only if it's less than 15 acres? Well, let's go with it. Let's go with 40 acres on this one. Land use is multi-unit attached residential. So from that, I can look up in a table what an appropriate C value is for that. And that looks about 0.5. So that means 50% of the water, the rainfall, will run off. Time of concentration, the D. Now again, there's calculations that go into this, and actually you have to, the rain goes from sheet flow to shallow concentrated flow, or the runoff goes from sheet flow to shallow concentrated flow to channel flow. So there could be a whole lot that goes into this calculation, but I've done that calculation and I've come up with 30 minutes for my time of concentration. So I go to the IDF curve. I have an F of 10 years, that's given. A duration of 30 minutes, that's the time of concentration. So I go to the IDF curve, and at 30 minutes, the 10-year frequency storm is right at 1, 2, 3 inches per hour. So that's my I. I've chosen my C is 0.5. My I is 3 inches per hour. My A was the 40 acres. I plug that in, and I get 60 cubic feet per second. Again, an acre inch per hour is the same as a cubic foot per second. So then that's what I have to handle. So for example, how much for that 30 minutes, if it runs off at peak rate for 30 minutes, that's 108,000 cubic feet. So I can do that calculation for how much I have to handle. Generally, I have to provide retention so that post-development rate is not more than pre-development rate. Although in some watersheds around where I am, I live on a threatened stream, and some of the watersheds here, there's a map that identifies if you're in it. We have to have 75%. So our post-development has to be less than the pre-development. It has to be only 75% of the pre-development. I'm jumping in here. My house is right here, so it looks like I'm in the 100%. So if something developed around my house, then the post-development, and we're talking about the rate here, has to be equal to the pre-development. But I know that back at Messiah University, where I work, which is in here, we're in the 75%. So the post-development has to be 75% of the pre-development rate. So RR is the release rate. Return to your regular scheduled program. All right, so I will stop there, and then we'll pick it up with the NRCS method next.